In this video, we're going to look at atoms and their forms. Atoms make up all matter, and life consists of primarily 10 bulk elements: carbon, hydrogen, oxygen, nitrogen, and then phosphorus, sulfur, sodium, magnesium, potassium, and calcium. The carbon, hydrogen, oxygen, and nitrogen make up approximately 96% of all living organisms. And as we are looking through this chapter on chemistry of life, we will see how common those four elements are in most of the molecules of living organisms. So 96% is a huge amount of the human body. Now, if you think about that, the fact that we are about 78% water alone, water is H2O. So there's a lot of the hydrogen and oxygen that's actually found right there. The 3.5% of phosphorus, sulfur, sodium, magnesium, potassium, and calcium, a lot of those actually work as electrolytes in our body. So we have a sodium potassium pump that's really important in moving things up in and out of cells. Um, Calcium is really important, obviously, for our bones, but also for muscle contraction. Magnesium is another electrolyte. And then sulfur and phosphorus also are important components in like bones. So those are all things that are found in the human body in larger amounts. But we also consist of a lot of trace elements. So iron, for example, we have iron in our blood that helps with the hemoglobin and the transport of oxygen. And then things like zinc, and zinc is sort of a very micronutrient or micro mineral, I should say, that is found in the human body in places like bones and other areas. Deficiency in elements can lead to illness and death. That's why, for example, if you're eating your box of cereal, you'll see the nutrition information. So you can look at those trace elements and see if you are getting sufficient quantities of those. You know, a lot of things like milk and orange juice, they're fortified with calcium. If you're drinking a Gatorade, it's going to have potassium and magnesium and sodium in it. And then many of the other little trace elements like folate that's so important during pregnancy, those are specifically labeled in a lot of things that might be on the recommended nutrition allowances for women during pregnancy. What do we know about atoms? Well, we see this little picture down here in the bottom right, and this is a typical representation of an atom with the protons and neutrons found in the middle and the electrons moving around the outside in what look like little orbits. In fact, they don't move in orbits. They actually move in an electron cloud, and they move much more freely than in very defined circles, kind of what you see here. But this is just a common sort of traditional way to sort of represent the configuration, and it's good for purposes of thinking about the actual setup of an atom. So atoms are the smallest units of elements that retain the characteristics of that element, meaning that when you get down to the level of, for example, a hydrogen atom, a hydrogen always has one proton, and that is what gives hydrogen its identity and sort of its behavior, and is why it is classified the way that it is. So hydrogen would be different than something like, for example, oxygen. Oxygen has 8 protons, which gives it, or sorry, it has 6 protons actually, it has 6 protons, and it gives it very distinct characteristics. And anything with 8 protons is going to be an oxygen, so it determines the identity of it. And an oxygen and hydrogen, very different for a lot of different reasons. Atoms contain protons, neutrons, and electrons. The protons and neutrons, as I mentioned, are found in the nucleus of the atom, and the electrons are moving around the outside in the electron clouds. The protons are positively charged, neutrons do not have a charge, and electrons are negatively charged. This means the neutrons don't contribute to the overall charge of the atom. As long as the number of protons and electrons are the same, the atom will be neutral because the number of proton positive charges outweighs the number of electron negative charges. When an atom has gained or lost electrons, then it becomes an ion, which means it has a charge. And ions are often, as we will learn, involved in ionic bonds, which is when you have a positive and a negative and they are attracted together. And so if an ion such as, for example, sodium, which is symbolized with an uppercase A, N, and a lowercase a, sodium has a positive charge when it's in its ionic form because it has lost an electron. Now it has more protons than electrons, which means the overall charge of the atom is positive. And it's positive by 1 unit because it loses its 1 valence electron on the outer shell. So really important to kind of understand that the valence electrons are the outermost electrons. Those are the ones that are involved in chemical reactions. A negatively charged ion would be something like chlorine. And you'll see in a minute why I'm specifically using this example. So chlorine has a 1 negative charge. It is negative because it has gained an electron. So now it has more electrons than protons. Since electrons are negative, we have more negative charge than positive charge. So we have an overall charge of negative. Sodium chloride is table salt. As we know, when sodium, which is positive, gets around chlorine, which has a 1 negative charge, they are attracted to each other and they can form ionic bonds. So electrolytes are, for example, ions. So if you think about electrolyte drinks, things like Gatorade, they contain sodium and potassium, which has a 1 plus charge. Magnesium has a 1 plus charge. The salt portion of it will have negative chlorine ions in there. And so you're actually bringing extra ions into your body. An isotope is a form of an atom that has different numbers of neutrons. So if we have something like carbon 14, for example, which is used in radiocarbon dating to determine how old things are, like let's say you find a petrified tree or some fossils, you can try to do radiocarbon dating to determine the actual age of that. Also, radioactive isotopes play an important role in science and medicine. So besides the carbon 14, radioactive isotopes are used medically in a lot of different scenarios. They can be used to detect cancers and as tracers, to follow atoms through a system. So an isotope, basically, it's just a different form of an atom. There's not neutrons being gained or lost specifically. At some point, there have been some reactions that have resulted in different numbers of neutrons in there. So again, I gave the example of carbon 14. The typical carbon is carbon 12, which would have 6 neutrons. Carbon 14 has 8. We don't have different numbers of protons. Again, the number of protons is always consistent because if you changed the number of protons, you would change the identity of the atom.